China built a dam so massive it literally slowed down the rotation of the entire planet Earth. That's not a movie plot. That actually happened. And the physics behind it? It connects to figure skaters, neutron stars, your phone, and why you don't fall off your bicycle. Stick with me. Hey, I'm FactSpark. If you like ideas that break your brain in the best way possible, hit subscribe because we do this every week. All right, spoiler right up front. The headline is technically true, but also kind of ridiculous. And by the end of this video, you're going to understand exactly why. And you're going to understand it better than the journalists who wrote the article. Let's go. Here's something your physics teacher probably never told you. Every single equation you solved in school, the cannonball, the ramp, the pulley, all of it was a lie. A useful lie, but a lie. Physicists treat everything as a perfect, infinitely small point with no size, no shape, no rotation. A train? A point. A planet? A point. A spinning top? Also a point. And a point, by definition, cannot rotate. So every time something spins in the real world, your school physics just quietly ignores it. That's the gap we're filling today. We're doing an upgrade from basic point physics to the physics of rigid bodies, which is the branch of physics that actually describes the world around you. And this upgrade has two key words you need to remember for the whole video: rotation and angular momentum. Those two ideas are the entire story. But before we get there, quick question for the comments, and I genuinely want to know, did your school ever teach you about angular momentum, or did they just stick to straight line motion?
Drop it below, because based on what I hear, the answer varies a lot depending on where you grew up. So, what even is a rigid body? It's exactly what it sounds like. It's solid, not a gas, not a liquid, and it's rigid, meaning it doesn't deform like clay. Every point inside it keeps the same relationship to every other point as it moves. Your coffee mug is a rigid body. A book is a rigid body. A planet is a rigid body. Look around you right now. Almost everything you see qualifies. That's why this branch of physics is so powerful and so practical. Now, to actually understand rigid bodies, we need to briefly revisit the basics, because we're going to need them as building blocks. Bear with me, this part is short. In basic physics, the point physics, the three key quantities are position, velocity, which is how fast position changes, and acceleration, which is how fast velocity changes. But the queen of basic physics, the most important quantity of all, is something called linear momentum. It's simply mass times velocity. Why is it the queen? Because it's conserved. When two billiard balls collide, the total linear momentum before and after the collision is identical. Nothing is lost, nothing is created. That's it. That's the whole foundation. Now, rigid bodies have a new challenge. A rigid body isn't a single point. It's made of infinitely many points all connected together. The Earth, for example, has every grain of sand, every ocean, every mountain, all of them contributing to how it moves. Treating all of that at once seems impossible. So physicists do what physicists always do. They find a clever shortcut. Instead of tracking every single point, we find one special point that represents the whole body. That point is called the center of mass. It's basically a weighted average of where all the mass sits. For a perfectly uniform sphere, the center of mass is right in the geometric center. For something lopsided, say a dumbbell with more weight on one side, the center of mass shifts toward the heavier side. And here's the beautiful result that makes everything work. The motion of a rigid body can be completely split into two independent parts. First, the translation, the whole body moving through space, which behaves exactly like a single point at the center of mass, following the basic physics rules we already know. Second, the rotation, the body spinning around itself, which follows a whole new set of rules we're about to learn. These two motions are independent. You can study them separately. The translation part, you already know. So everything that's new is just the rotation. And as you'll see in about 60 seconds, the rotation part is a perfect mirror image of what you already know. When something rotates, instead of measuring how far it travels, we measure the angle it sweeps through. Instead of velocity, we define angular velocity, how many degrees or radians it covers per second. Instead of acceleration, angular acceleration. Same structure, just applied to spinning instead of moving in a straight line. And just like linear motion has its queen, linear momentum,
Rotational motion has its own queen, angular momentum. Angular momentum is the rotational equivalent of linear momentum, and it is also conserved. That conservation is the entire engine behind today's story, so let's make sure it really clicks. Angular momentum depends on three things: mass, velocity of rotation, and this is the crucial one, how far that mass is from the axis of rotation.
The further the mass is from the axis, the more angular momentum it carries. Think about a classic lever. A small force applied at a long distance can lift a huge weight. Distance from the axis matters enormously. And now, bundled into a single quantity we call the moment of inertia, we capture both the mass of an object and how that mass is distributed around the rotation axis. The moment of inertia is to rotation what mass is to straight-line motion. It's a measure of how resistant a body is to changes in its spin. And here is the single most important difference between mass and moment of inertia. Mass is fixed. You can't change the mass of a rigid body without physically adding or removing material. But moment of inertia can change, just by redistributing where the mass sits relative to the axis. Hold a notebook flat in front of you. Now roll it into a tight tube. Same notebook, same mass, completely different moment of inertia. Move weight toward the axis and the moment of inertia decreases. Move weight away from the axis and it increases. This is the key to everything. Now, let's connect all of this to the thing you've been waiting for. The Earth is a rigid body. It rotates around its own axis once every 24 hours, and it does so with a fixed angular momentum. Because angular momentum is conserved, remember? And nothing significant is pushing or pulling the Earth's spin from outside. That angular momentum equals the Earth's moment of inertia multiplied by its angular velocity. These two quantities are locked in a seesaw. If one goes up, the other must come down, because their product, the angular momentum, stays constant. So, China builds the Three Gorges Dam. Water from downstream, sitting relatively close to the Earth's equator at a low elevation, gets stored in a massive reservoir. That water is now sitting higher and, crucially, slightly redistributed in terms of its distance from Earth's rotation axis. The moment of inertia of the Earth increases, even slightly. And if the moment of inertia increases, angular velocity must decrease to keep angular momentum conserved. The Earth spins fractionally slower. The day gets fractionally longer. This same principle explains so many things it's almost absurd. Think about a figure skater spinning on ice. She pulls her arms in. Mass moves closer to the axis. Moment of inertia drops. Angular velocity shoots up. She spins faster. Every single time you've watched that happen, you are watching angular momentum conservation in real time. Same thing happens with stars. A star is born from a slowly rotating cloud of gas. As gravity pulls that gas inward, as the star collapses, its mass moves closer to the axis. Moment of inertia plummets. Angular velocity skyrockets. The most extreme version of this is a neutron star, a collapsed stellar remnant so dense it fits the mass of the sun into a sphere the size of a city, spinning hundreds of times per second. The same physics, the same equation, just at a cosmic scale. Your smartphone uses this too. Inside it, there's a gyroscope, a small spinning mass whose angular momentum resists changes in orientation, which is how your phone knows whether it's held vertically or horizontally. Satellites use gyroscopes to orient themselves in the vacuum of space without any atmosphere to push against. And your bicycle stays upright while you're moving because the spinning wheels carry angular momentum. When you try to tip over, that angular momentum resists the change. The faster you ride, the more angular momentum, the more stable you feel. That's why wobbling at low speeds is so much harder than cruising fast. Now, back to the headline. Is it true? Yes. After filling the Three Gorges Reservoir, the Earth's moment of inertia increased slightly, and its rotation slowed slightly. The day got longer by roughly 6/100ths of a microsecond. That is 0.06 millionths of a second. The headline was technically accurate, but here's why I said yes and no at the start. First, the whole point of a dam is that the water eventually flows back through turbines and downstream, so the effect reverses. And second, the amount of water involved is cosmically trivial compared to the total mass and size of the Earth.
The change in the day's length is so small, it's unmeasurable by most instruments on the planet. To put it in perspective, every time you pick up a glass of water and put it on a shelf, you are also slowing the Earth's rotation. Every time you climb a flight of stairs, you are shifting mass away from the center and increasing the Earth's moment of inertia. You are technically lengthening the day. You, right now, reading this. The physics is real. The effect is just so infinitesimally small that it vanishes into the noise of everything else happening on this enormous, restless planet. And I think that's actually the most beautiful takeaway from this whole journey. We started with a viral headline about a dam in China.
We ended up touching figure skaters, dying stars, your phone, your bicycle, and the fundamental architecture of how rotating objects work throughout the entire universe. That's the thing about physics. Pull on one thread, and the whole tapestry comes with it. Angular momentum is conserved. The further mass is from the axis, the more it carries. Change the distribution, and the spin changes to compensate. That's the whole story. 3 sentences, an entire universe of consequences. I'm FactSpark. If this cracked something open for you, share it with someone who thinks physics is boring. They're wrong, and now you can prove it. See you in the next one.